In this video, I want to talk about distributions. So in the last video, I talked about probabilities of random variables, variables taking the probability that a variable takes a certain event. And now we're going to talk about it in a bit more detail in distributions. So a probability distribution describes the probability of each possible outcome for a variable. So for a discrete variable, that gives you a single probability for each outcome. Right? So a discrete variable might be a dice, yeah, and each side has a 1 in 6 probability. Right? So the discrete distribution would be literally throwing a 1 is 1 over 6, throwing a 2 is 1 over 6, 3, 1 over 6, 4, 1 over 6, 5, 1 over 6, and 6, 1 over 6. A continuous variable is usually a form mathematical expression that describes probability for a range of outcomes. We can distinguish between empirical and theoretical distribution. So empirical distribution, empirical means based on data. Empirical distribution is merely describing the observed data. So it's usually like a histogram of the data, or like what's the data telling us. A theoretical distribution, on the other hand, is some mathematical formula that uses some parameters, like the mean, for example, describing where the distribution is placed, that describes probability of each outcome. If you have the theoretical distribution, we don't need the empirical distribution. And the problem is we often don't have the theoretical distribution. We need to estimate some data. We don't know the exact mean, we don't know the exact variance, for example. Okay, so let's look at an example. So here I have happiness scale. It's a scale from 0 to 30. Say I asked several questions, yeah, and I took a sum score. So maybe I asked 10 questions that could be scored 0, 1, 2, and 3. I summed them, and each of my participants here, they're all AI generated cute animals. Each of my participants here has some score. Okay, so maybe at 23, there's only one shark, and the shark scored 23 in happiness. At a score of 4, this dolphin and this elephant, they're very sad, really, really poor animals. Yeah, but most are actually scoring somewhere in the middle. Now we could draw a bar over each of these and make as high as the number of participants. And so each participant is now equally big, so that's easy. So we have here 1, 2. Right, so that's a height of 2. We see that there are 2 participants who score 6. Right, and here, how many are there? 1, 2, 3, 4, 5, 6, 7. There are 7 participants who score an 8. Right, the most participants are scoring this one: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you remember, that's called also the mode, the highest peak in our distribution, and etc. etc. So this is a histogram or an empirical distribution. Right? Normally we would not draw the pictures here, but yeah, we now include them just to show it. This is what we call an empirical distribution or a histogram. In this case, I use a bin width of 1. The bin is the size of the box of the bar, and 1 means okay, only one value goes in. Now this usually creates a bit of a ragged distribution, right? It's like very peaky, right? There's like some sort of like gap here, just because of random chance. We could create a histogram with a bin width of 2 instead. So now the size of each bar is 2. Right, so in this case here, this only includes 2. But here we have 4. Include 1, 2, 3, 4. So that's why the height is now 4. And here we include, many, right? So that's why the height is really big. The bigger we make our bin width, the more we capture the general pattern. But at some point it just becomes too big. Right? At some point we just get like 1 bar, for example, that's too big. So you always have to choose a bit carefully. How big do you make your bin? How big do you make it? Okay. Now we can use our empirical distribution to calculate empirical probabilities. Empirical probabilities are simply how often does something occur in the data. In this case, let's get the empirical probability of happiness being less than 10.5. 10.5 being here this cutoff. How do we calculate that? Well, we take the number of animals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 23 animals. We divide it by the total number, which is 100, believe me. And we get this value 0.23. So 23%, in this case there are 100, so percentage is equal to the number. 23% of the subject scores happiness below 10.5. Now, a theoretical distribution would be some mathematical formula that tries to approximate this shape. In this case, we would try to use a normal distribution. A normal distribution is this nice bell shape. You can see this as basically taking this bin width even smaller, smaller, smaller. Of course, now we can't make it smaller than 1, but suppose you could have happiness on like a very small scale, 0.01, 0.02, you can make it even smaller. So this generally matches this pattern of the histogram. Right? Now we need to place it, so we need two parameters here. The mean, standard deviation. The mean is what controls the center point of this distribution. Yeah. The standard deviation, this one, is what controls the width distribution. The larger standard deviation, the larger the width of the distribution. The mean says, okay, where is the average? Now, using this formula, we can now try to get the same probability. Right, so now that I plugged in the mean and standard deviation based on the sample. But maybe you don't have to, maybe you already know the mean happiness scale. Right? Then you can use that. But now we use the sample mean. And that's a pretty important topic later in the course as well, actually. Using this distribution, we can look at the area to get the probability. So this red area here, it's literally the area, the size of it, if we would standardize this y-axis to be probabilities. The entire size is 1. Total law of probability. Something must happen, right? So getting any response from 0 to 30, in this case, should have a probability of 1. So the entire area under the curve, under this whole area here, really, the whole area here, should sum to 1. Then we can look at, okay, how big is this selected area of the area we're interested in, how big is this area relative to the total area? We can calculate the size of this. Yeah, that's like, you might remember that from high school mathematics. Can be actually pretty complicated to do that. You need to check integrals and stuff like that. I'm not going to talk about how you do that. Just you calculate the size of this, how big is this? And so one thing you could do is just approximate it. Okay, this is like, here's a bar, how high it does, and then some DOS heights. But there's a better way to do it in JS, which I'll show. And that probability gives us the probability according to the theoretical distribution of scoring below this 10.5. And you see they're very similar, right? It was 21% here, 23% in the data. Right? That could be the case. In this case, we are assuming also that there's normal distribution. Right? So we see actually this peak here is a bit of an outlier to our normal distribution. But that can definitely happen. Sample size of 100 is not that big. If we have sample size of much more, then we would expect a much more smoother bell curve to occur. So let's actually look at a larger sample size. What I have here is a Galton board. And basically how it works is we have little pins here. And we have balls on the top. And they fall through this hole on the first pin. They go at random left or right. Then they fall on here, they go at random left or right. They fall on this third pin, they go at random left or right until they end up in the bottom in one of the boxes. Right, so here, left, right, here, left, right, here, left, right. Where they end up in the bottom is actually a sum score of random independent events. Left, right, left, right, left, right. They're all the same shape. So yeah, that's actually, you can just sum how often they go right to get where they end up in the bottom. We have a lot of these balls in here. A lot of them. So let's see what happens. going to flip it now. And I'm not holding it perfectly straight, but you see that they're actually following this bell curve. Let's try to do it again. You see that they're following this bell curve. And it's now much more smoother. These are a lot of events, so you would actually expect this to follow the bell curve really closely. It follows the bell curve because of something called the Central Limit Theorem. It's a really interesting thing. I'll talk a bit more about it later. But basically, if you sum independent events, then you will always end up with a normal distribution, which is like really quite amazing statistical thing. But I will not talk about this now. Now, there's some distributions that we're going to use in this course. We're not often going to use them directly. I'm not going to ask to get probabilities directly, but they're the distributions that are used to get the p-values. So that's why you should know of their existence. The main one is the normal distribution with a mean and a standard deviation, which is this bell shape that you should be familiar with. The student t distribution is a distribution that we get when we have to estimate a variance. So, for example, we might want to test is a mean in a sample 0. So we have a distribution around 0. We know 0 because that's the point we want to test against, but we don't know the width of the distribution of this distribution of the mean. If we want to estimate it from the data, then you end up with the student's t distribution. Chi-square distribution, which is this distribution that's for variances actually. That's positive, but never below 0. And the f distribution, like the t distribution, assumes that we don't know true variances in the population, we need to estimate them. The f distribution is what we're going to use a lot in this course. We'll often report our results with f tests, or t tests actually for parameters, or f tests for model comparisons. I'll talk about that more later, but yeah, this is what it looks like, and actually you have also some shape like this, but it's basically always positive as well. Some other distributions that we don't use in this course, but they are important. The uniform one is just a fixed range between two values. For example, the model probability between 0 and 1. And the beta probability actually extends this to also other shapes between 0 and 1. It can even have like a bimodal distribution, for example. Exponential distribution, which models is always positive, models a decline, exponential decline, like first very high probability of few things occurring and a low probability of many things occurring. Like earthquakes are exponentially distributed, for example, where there are some earthquakes that occur that are very strong, but most of them are weak. Poisson, or count variables, so if you have count the number of times something occurs. Gamma, is for variances, if you want to model a variance in a Bayesian setting, for example. And binomial, that's a really important one. That's to model the amount of times something occurs in a fixed set. Right, so Poisson and binomial are a bit different. Poisson is just about a number of times something can occur without being a fixed set, and binomial is a fixed set. So we have 10 throws. How many times do we throw a head? And that could be 5. Right, the Poisson distribution could be about how many times did you go out of the house in a certain period of time. It could be any number. And here we have the probability of throwing heads. If you throw 10 coins, right, we expect 5, but it could actually be 8 or 9 as well. Okay. Now, how do you get probabilities from distribution? That's actually pretty easy to do if you use software. I mean, the old way to do it is to have a table. Right, and for exams, that's sometimes needed. We're not going to have that in an exam this course, so you don't have to do that for this course. So I just want to show you how you can do it with JASP. So let's dive into JASP to see how it works. So this is what JASP looks like. When you watch this video, maybe it's a newer version, but it's basically what it looks like. And when we're collecting data, we go to new data, we enter our data, or we upload data using the menu. Then we can press all these analysis buttons to analyze the data. I have test model because I'm developing stuff, but you don't probably have that. But we're going now to plus, then we can add more modules, and there's a lot of them. A lot of different things are implemented that you can add still to JASP. We go to distributions, and we can also enable learn stats. which is a nice module as well. Now in the distributions menu, we have all these distributions that we can choose from, like binomial, things like that. Let's just go to normal. So you have here the normal distributions. You have to enter here the mean and the variance. So let's take an IQ test. You have a mean of 100 and a variance of 15, for example. And then let's say we want to look at that from, let's say, 50 to 150. But now we have this distribution between, well, let's do 80 and 120. 20, yes. So now we have this distribution, normal distribution for IQ test between 80 and 120. And let's say we want the probability that you have an IQ above 105. You say, okay, probability from 105, doing this symbol stands for infinity, so all the way to the right. We get a probability of 0.1 in this case. Can we add some more things to that? All kinds of explanations as well. Other things you can do as well. You can look at the cumulative distribution function. So this basically, what this is the probability if we look at, okay, the probability to the left of a certain point. So for each point here, the probability to the left of the point. We'll talk more about that later. The cumulative function, and we see here, okay, for 0.5, 0.90 is below that. So 0.1 is 1 minus 0.90. We also have this really nice learned stats module. So let's look at the normal distribution there. And again, there's some nice explanations as well. And if you have a data set, actually, we can also display the data and estimate the parameters and look at the fit of some things as well. Here, basically this works the same. So we can look at the probability between a certain range in the standard normal between 0 and 1. What's the probability between -1 and 1? You get a certain probability like that. Very easy to do. You don't have to look up any fancy tables or anything like that. Okay, that's it for this video on probability distributions.